For almost 2 years, this channel has been explaining how various game engines render real-world video game graphic scenarios in order to find out what optimized and non-optimized games have in common. And well, me and my team found those commonalities. After several requests on our channel's content from both our gamer and developer following, and confirmed content demand via Patreon polling, we are here to take a break from our analysis and industry discussion content to explain how modern games should be rendered for optimal performance and visual quality. This video is intended for both gamers and developers. Gamers need to watch this video for 2 reasons. The first reason is similar as to why you would learn the basics of your own car. If you take your car to a mechanic to get a broken window motor fixed, most likely that mechanic will try to jack up the price on a fairly simple job. If you learn a bit about the actual steps to fix that motor and search the part price yourself, you're going to see that mechanic is charging you several $100s more for what you can tell is pretty simple labor. So, you can either haggle with a mechanic for a better deal, or you can fix the window motor yourself. Now, as a gamer, you most likely won't be able to fix poor graphic pipelines, but you can haggle by calling out studios or influencers that try to gaslight you into thinking ugly-looking graphical practices are optimizations. A consumer that challenges abusive and ignorant graphics lowers the market value of titles adopting such poor techniques. And a consumer who creates tangible demand by requesting what's shown in this video raises the market value of real optimization. Market value is the second reason why you have to watch this video. You are the market, but you have to realize a lot of other people are willing to purchase garbage, so studios have very little reason to take optimization seriously. A studio needs a market that incentivizes and rewards their graphics development. If a studio advertises that they implemented a non-alpha tested partial prepass, that advertisement, that marketing, only works if you know how great that is. And you're going to learn about that term I just mentioned, along with a whole lot of other things you'll want implemented in your game. As for developers, this is clearly helpful for graphic engineers, but say you're a developer who doesn't work in the graphics field. This video will help you know what to demand from your engine distributors, whether that's a department within your own current studio or a major licensor. Alright, so we're going to be using this graphics pipeline diagram to show all the information we need to discuss. I'm not going to read everything that's in this file because that would be redundant, as most of the information here was already discussed in previous videos. I'm just going to share context about certain decisions, new information about certain pipelines missed in previous analysis videos, and show how to advertise related optimizations. It is highly recommended that you have this free diagram file loaded on your desktop as I go through this video. We highly recommend that you have this pipeline chart and follow along as I go through this video. This chart took us 1 month to create, and this video represents 3 months of production time. It is available as an exclusive gift to all tiers of our Patreon members. We seriously need your support, and we are so thankful to our current members. This pipeline accommodates for a very specific yet common technical scenario, and targets specific hardware and visual standards explained in previous videos. You can either blindly adopt these common sense standards now, or watch the various videos included in the description explaining these standards. The chart progresses from left to right, so we'll hold Control while scrolling to zoom up on the beginning. I felt that separating the discussion into 3 different layers would help break apart the data in a more digestible form. The middle layer is a step-by-step description of what graphical passes your GPU should process per frame. This is analogous to the graphs seen in our analysis videos and only pertains to GPU processing, as that's where most of our research is relevant. The top layer contains the related workflow nodes. This is a massive area of development many people ignore. It doesn't matter how excellent or optimized the graphics pipeline is if the game engine doesn't provide specific workflows for artists. The bottom layer explains the related issues we avoid, what visual goals we achieve, and what pipelines showcase the poor/optimal viability of said approach/pass. Now originally I wanted to discuss graphic APIs such as Vulkan, which really aligns with the open standards we advocate for. From a pro-consumer view, it's optimal, from a development point it's optimal, but from an optimization point it's tough because the optimization debugging tools for Vulkan aren't as matured as the DX11 tools. So 2 different paths might need to be developed. Right now we need more testing comparing DX11 and Vulkan performance, as some of our testing has shown that hardware shades pixels 2 times faster with DX11 than DX12, and we're currently concerned that Vulkan may perform more similarly to DX12 in terms of shading efficiency. But because our testing has been limited to Unreal Engine's API implementations, there is a chance this could just be an exclusive failure on Epic Games' graphics management. A failure DX12 and Vulkan could potentially overcome if the issue is identified. Fortunately, this doesn't impact the core topics of this video. I just wanted to share a few thoughts regarding APIs. Okay, so let's start breaking down the first step. We have our pass title and pass description boundary. The gray description boundary indicates more testing could lead to a different way of managing its said contents, such as being moved later in the pipeline or being removed entirely. Text boxes inside the pass description boundaries act as steps describing what actions the GPU performs within this pass. Later on, we'll encounter passes containing multiple steps. Sometimes these steps are labeled. Red text boxes indicates more custom in-engine tests are needed, which could lead to changes in the approach. Connected question mark tags indicate we have some thoughts to share about the topic, but need to complete a related video before discussing its factual content. It can also indicate more optimization research via custom in-engine implementations are needed. I want to discuss why starting frame compute shaders were brought up, as plenty of pipelines don't actually have them. Basically, modern games are trying to move a bunch of traditional CPU tasks to the GPU, like animations and geometry management, but we're not moving anything from the GPU to the CPU. So modern games are making the GPU work more, even though plenty of other games in the past have done just fine with minimal GPU-driven systems. The reason why there's such a mainstream effort in moving CPU tasks to the GPU is because we are bloating our CPU pipelines with unoptimized code and languages like Unreal's blueprints, which have been known to be up to 10 times slower than its C++ counterpart. One of the most influential GPU-driven pipelines was created for AC Unity. They couldn't have the CPU-managed geometry like most pipelines because they spent so much CPU resources on massive crowd animations. Just think about these three things. That is not a popular technical scenario to cater towards. We're targeting 9th gen CPUs now, not 8th gen, and the NPCs in that game looked terrible. So do we really want to spend tons of computing resources on dense crowds of garbage? More reasonable NPC counts with higher quality appearances, akin to something like we've seen in KCD2, is a much more sustainable approach. Anyways, there's a few reasonable processes to manage at the start of the frame with compute shaders, but these processes need to remain very small. The main point here is that the GPU pipeline needs to process a lot of steps, and it can only process so many things. Do not bloat it with actions the CPU can handle instead. I also want to make sure people know I don't have an issue with visual scripting systems. I simply think more investments need to be made in bringing its efficiency closer to native C++. I definitely think that is possible, and I think performance comparisons of different visual scripting systems would incriminate UE blueprints, which in turn would raise demand for such a massive software renovation. Moving on to the next pass. So what is it, and why is it so important? When you render geometry, that data is stored on a resource usually referred to as a buffer or render target. Usually, a specialized accelerated hardware function will clear that digital resource before everything new is rendered on it again. These clears are typically completed at the start of the frame or before its corresponding pass. While more testing is needed for shadow and effect resources, the deferred G-buffers like base colors and normals, which would also exist in a complex SSR-supported forward plus renderer, don't need to be cleared, because as long as the depth buffer is cleared, the other outdated information can just be overwritten with pixel-perfect accuracy. Many engines don't take this seriously, but we want our GPU to overwrite pixels instead of clearing and then writing pixels, because that writing action is effectively a free clear for whatever pixels that object invokes. Effects can suffer from poor clear management too. Like this ambient occlusion pass that clears the ambient occlusion output, instead of letting the pixel shader invocations in the next pass overwrite the current values for free instead. It's something to be very conscientious about, but a few G-buffers should still be hardware cleared, such as the emissive diffuse buffer. You have to clear this because you will not have the opportunity to overwrite its entire surface area, as only emissive objects/materials will get the chance to write data to it. We don't have to clear the specular RGBA16 because it's overwritten/recycled in a later pass. It may be best to clear any buffer where MSAA coverage information is stored. It made sense to store it with motion vector data, as both will be relevant in later anti-aliasing stages. But more on this later. You'll want to clear the dual normal buffer, which exists for Callisto Protocol character rendering research. It needs to be cleared because, like the emissive diffuse RGBA16, you will not have the opportunity to overwrite its entire surface area, as it will only be called when certain materials, like skin, appear. Having an accurate stencil stored in the 2-bit alpha for later stages could end up being pretty helpful. The advice here is applicable to any genre, deferred rendering or forward plus renderers. And there's nothing about this topic that should require configurations from studio members unless an artist wants to recycle a resource for some effect later on in the pipeline. The term hijack clear is used in the notes here, and this means hijacking a process in the last frame and telling a shader, hey, while you're writing data to your main output, simultaneously, meaning for almost free, overwrite some additional outputs with data equivalent to a clear. This was a really cool trick I wanted to bring attention to. The next thing I want to mention, even though some people will wrongly whine about how this is so-called common knowledge, a full-screen triangle should never be used to clear a render target. I've seen it too many times in our analysis videos and pipelines to not mention it. Using quads or triangles will always be slower than a hardware clear, at least on modern hardware. You will destroy performance doing this. Now the last thing I want to mention for resources that do end up being hardware cleared is that they don't tend to be equal across pipelines. A cool detail that didn't make it into our KCD2 analysis was the fact that it cleared resources such as the native RGB A8 2 to 3 times faster than most engines, including DX12 UE5. Speaking of UE5, I have found its hardware clears to be incredibly inconsistent, such as this clearing action done for the UE5 tone mapping stage output, which could have just been overwritten akin to Crysis 3's post-processing stage. Now let's actually take a moment to address something real quick, because I already see low IQ haters coming up with some fake gotcha a mile away. They're going to add up that inconsistent clearing cost with that UE5 tone map draw timing, and point out that this UE5 tone mapping is faster than the Crysis 3 processing draw, even though it's not using full screen overwriting to skip the clear. So the tone mapping Crysis 3 draw in this comparison is more expensive because unlike the UE5 tone mapping draw, the Crysis 3 draw is integrating a bunch of filmic functions, resolving a bloom resource, and upscaling half-resolution volumetric fog. It's merging all these functions with tone mapping as an optimization we'll explain more about later. But the reason why this would be such a low IQ gotcha is that even if the UE5 draw was functionally equivalent and faster, this would still not invalidate the advice being given here. I'm using a 13-year-old tone mapping akin stage for mere theme, but I could reference a full screen overwrite technique used in Need for Speed 2015's HBAO pass, and it would still be a good example of an older game optimizing its performance more than newer games by skipping an unneeded clear. No one is low IQ if they have a question. I will gladly answer genuine comments below, but it's absolutely low IQ to take our points and pretend to have some so-called ironic gotcha because they lack basic comprehension skills. As a good faith viewer, just be vigilant of that kind of idiocy, because we don't have the resources or time to constantly correct such stupidity. Do not underestimate the advice being given here, because if you're able to save just 0.1 millisecond, which would probably be the minimum performance enhancement you'd get from implementing this, that can make a huge difference for something like lighting or higher quality anti-aliasing. Micro optimizations like this are going to stack up. If you're trying to promote a game or engine, you should make posts discussing your product's hardware clear cost, full screen overwrites, and hijack clears with hardware and resolution specifications. The less powerful the hardware and higher the resolution, the more impressive. If you need time to implement this advice, document performance improvements as an advertisement for your product. Here on this channel, we're doing our part explaining the importance of these techniques to your customers. We're raising the market value of these optimizations, but studios have to do the actual marketing. But as a consumer watching this video, now you know what to look for. Now timings in the lower right corner of some past descriptions indicate a maximum cost studios should aim for. Again, reference the slide shown earlier for resolution and hardware context. Green text down here indicates we're learning positive attributes from various products. Red text means we're avoiding visual or performance issues discovered in past analysis videos. Okay, so let's discuss the next stage of rendering. This right here is something that can make a huge difference in our performance. Now the title for this pass might be self-explanatory for some of our more experienced viewers, but let's dive into some context that puts us all on the same page. You can first look at GPU performance as almost scaling with the amount of pixel surface area we've shaded. There are two ways your GPU can shade pixels. With compute shaders, which can be used for anything on the GPU, but when shading pixels, use computational grids that range from 1-dimensional to 3-dimensional functionality. Or you can rasterize a triangle across a grid of pixels and invoke a specialized pixel shader wherever an intersection is successful. I said GPU performance almost scales with the amount of pixel surface area we've shaded because the actual bottleneck is a product of the total surface area shaded and its retrospective shader efficiency. So you could shade 2 million pixels with one shader and have it cost 0.3 milliseconds, then have two other draws process 2 million pixels each, but together only cost 0.2 milliseconds. It wouldn't indicate that the first draw is unoptimized. It could just mean that either the output requires much more complex arithmetics and or requires a lot more bits worth of input data, which is called throughput, because it's the amount of input bits going through a shader. The shader efficiency per pixel can be optimized in a few ways independently of arithmetic/throughput complexity. There can be shader logic that cancels operations if that certain pixel isn't in need of such processing. A mask or tiled resource can tell a compute shader, hey, cancel any operations in that certain area. This is called branching, and even though they might prevent expensive operations, branching in GPU code can slow the overall shader performance. And these techniques don't come anywhere close in terms of speed as depth stencil testing, which is a feature exclusive to traditional triangle rasterization. Remember how intersections gained from rasterization invoke a pixel shader? Depth testing allows us to almost instantly cancel or allow pixel shader invocations based on information and functions related to corresponding values stored in the depth buffer, such as checking if pre-existing geometry is occluding the rasterized pixel to cancel its pixel shader invocation. You can also use additional or standalone functions based on values stored in the depth buffer stencil channel, such as preventing skin lighting on non-skin materials. Again, remember that you can use both stencil and depth testing at the same time or independently, as our pipeline is heavily dependent on stencil channel management. When you render a geometry pass like a deferred gbuffer basepass or a forward plus basepass, even if the geometry draws are properly z-sorted from front to back, you will still end up with tons of overdraw, which is the overlapping of pixel surface area shaded. But by the end of these passes, you will have your final depth. If we had the final scene depth before we render the base pass, we could prevent all this overdraw using depth testing's equal to function. A prepass is an approach at getting that scene depth information early by rendering the same objects beforehand and only rendering their depth information. This means overdraw only resides in the depth prepass, but this is supposed to be better because depth-only information can be rendered way faster, so it can chew through surface area overdraw much more efficiently. In fact, motion vector passes and visibility buffer alike solutions can chew through surface area overlap as well, and generally function as additional or replacement prepass approaches. The only reason why the visibility buffer in UE5 is slow is because they use mesh shaders instead of vertex shaders for large triangles, and compute shader software rasterization for micro-poly clusters, both of which we proved are horrifically slow to process, partly because of broken or completely missing hardware depth testing. Speaking of slow performance, the process of re-rendering everything with depth to rid our more expensive stages of overdraw is not all cookies and rainbows. These stages are somewhat immune to overdraw, but the efficiency of these can plummet due to two other factors. The first reason is related as to why they're so fast in the first place. They don't sample any textures. Motion vectors, visibility data, and even an ALU 2x2 Bayer matrix dither all require arithmetic processing, which is really cheap on modern GPUs, unlike sampling a texture per pixel, which none of these do until you start processing alpha-tested content, like foliage or hair, because each pixel is forced to fetch an opacity map value. When you start sampling an opacity map, the cost of the prepass draw becomes too similar to its base pass counterpart. We saw this in our Days Gone analysis, but let's take a look at Crysis 3, which uses a partial alpha-tested prepass. Partial because it doesn't draw distant geometry for reasons we'll explore in a few moments, alpha-tested because it's prepassing alpha-tested content. But let's take a look at this large alpha-tested tree. It provides a great amount of depth surface area for our deferred base pass, but its retrospective base pass draw is really similar in cost, even though it's accessing two larger textures and outputting way more render targets. This is because GPUs process things in the most parallel way possible, and of course it's a little bit faster than its depth prepass counterpart because the depth testing function is preventing invocations where alpha testing previously failed. I could explain this at a more granular level, but honestly, we have professional tools that just let us see the results via testing instead of babbling about theoretical performance this or that. This alpha tested draw costs 0.13 milliseconds with a pre-passed counterpart. If we disable its pre-passed draw and enable the same depth function on its standalone Basepass draw, that asset's total performance cost becomes at least 13% faster. Even if you disable all the draws in between, which I'll explain why this is shown here later. But that 13% is actually boring until you realize that's the draws cost with depth writing disabled. This means only pre-existing depth is preventing invocations, but it's not writing its own depth, which means it's not helping its own performance with additional depth surface area like a real-time alpha-tested draw would. Its cost is massive because it's blindly overlapping the mesh triangles, hence its own material surface area. When we take the extra steps to ensure depth writing is enabled on the draw, now we see that its performance is nearly identical to the pre-passed cost, which means if we only wrote the Basepass draw in place of the pre-passed draw, we would increase the efficiency of this draw by 40%. Imagine that level of performance enhancement on a whole scene of alpha-tested content. Now, there are two issues people may raise about this test. The pre-pass, and in turn the original 0.13 millisecond cost, might be lower if this pipeline didn't output vertex normals. That's not going to make or break pre-pass performance. It's going to have the same efficiency as those passes I mentioned earlier. The last issue will probably center around the fact that the Basepass draw isn't actually alpha tested. The pixels rendered cost being higher in the non-alpha tested draw than the pixel shader invocations number in the alpha tested draw indicates the Basepass draw is doing more work. But you know what? We got another example with a purely depth-based prepass and a massive G-buffer layout. This asset incurs a 0.6 millisecond cost with a prepass counterpart and only cost 0.44 milliseconds without. And this time the Basepass draw is actually alpha tested, and for some reason I can't get this draw to write its own depth. So obviously, that's only going to increase performance even more in a properly configured non-debugging scenario. Let me remind you that KCD2 broke the internet for the amount of foliage it could render, and that game only partially prepasses alpha-tested content, and gained performance when we disabled its prepass in-game. Still think this Silent Hill 2 remake test isn't good enough because the draw makes up 250,000 triangles? Well, the geometry bottleneck test doesn't indicate that the geometry is the biggest issue with this draw, unlike the invocation stats. But hey, let's test a huge amount of slightly unoptimized yet lower poly foliage assets, still faster without prepassed counterparts, even with all that scary overlap that still exists in the prepassed without showing you when you allow alpha-tested prepassing in Unreal. Let's analyze the performance of dense cutout alpha-tested geometry, still slower with prepassed counterparts. There are only two online encounters that act as potential discreditors to this advice. This video of someone gaining around 30% more performance by including alpha-tested content in the prepass and advice given by Guerrilla Games. That video lacks too much context. There was no concrete indication UE wasn't automatically upscaling from a lower resolution using its temporal upscaler, or maybe there was a sorting issue in which the method we're proposing here would work far better. As for Guerrilla Games, remember that Decima Engine games run 30 FPS on PS4 in comparison with Fox Engine titles. In other words, we're working on some content that challenges that studio's research even further, so stay tuned for that. Now the other thing that can harm prepass performance is quad overdraw / dense geometry. This is a separate issue from those overlap heat maps. Pixel shader invocation counts are sort of a lie, because pixel shaders actually work in 2x2 pixel groups called quads that work in parallel. A more honest metric would be quad invocations, as that's what we want to minimize instead. If one pixel requests more samples or arithmetics than the other pixels could finish and then be forced to wait for the complex pixel before moving the whole quad on another set of 4 pixels to work on. This introduces something called quad overdraw. Let's say we have a diamond-shaped mesh made up of 2 triangles. The GPU will rasterize the first triangle, invoke the appropriate pixel shaders, and have some pixel work wasting away on the edges. When the GPU rasterizes the next triangle within the mesh, it invokes quads again in the same location, So we're overlapping slash overdrawing quads. Modern affordable hardware can handle a lot more quad overdraw than previous console generations. But when 70% of our material surface area starts exceeding 3 out of 4 failed quads, that's when non-texture sampling geometry passes start crumbling and having performance issues. You know, the internet right now is filled with all these Epic Game damaged controllers that don't showcase LOD quad overdraw when comparing to nanite performance, because it would expose how unoptimized their LODs are and how much performance their LODs are leaking via redundant quad invocations. And they certainly never show the pre-pass setting, because pre-passing can act as a 2x quad overdraw multiplier for dense geometry. That's why it's so funny when you see these UE tutorial morons showing the quad overdraw view mode on nanite meshes, because it writes Basepass data using quadless compute shaders or a flat low poly geometry plane that references the visibility buffer, both of which, of course, we proved performed equivalent to really bad quad overdraw. Anyways, we don't want to pre-pass distant geometry because they get so small on screen. Even with good LODs, we'll end up paying too much in quad overdraw cost for pretty poor occlusion data. Pre-passing geometry doesn't help the overdraw cost that is bound to exist in the Basepass counterpart draws. So only large slash close geometry should be pre-passed with pure depth rendering. Using various game examples, this is what the pre-pass result should look like. Make marketing use of this technique by sharing images of your game and their retrospective pre-pass depth outputs. Customers should look for large amounts of depth surface area rendered with relatively simple geometry, determined through additional wireframe or pre-pass quad overdraw debugging views. Ensure your customers that no per-pixel texture sampling is allowed in the pre-pass, such as alpha testing or per-pixel displacement. I will say though, Fox Engine has shown the viability of per-vertex displacement using textures through its terrain approach, but that's likely dependent on minimal quad overdraw. It should remain under 0.3 milliseconds, as that's what Half-Life Alyx is able to achieve while processing a full non-alpha tested pre-pass in heavily urban scenes. A partial pre-pass is one of the reasons why deferred rendering was chosen for this video opposed to Forward Plus, since the latter usually demands a full alpha tested pre-pass. It's not the only reason, as a lot of it has to do with micro detail issues and redundant MSAA shading deferred rendering can actually overcome, but Forward Plus rendering is not entirely out of the picture, as internal conversations with consultants and channel followers have led to discussions about maybe not requiring a full pre-pass for Forward Plus. And after a certain point, a Forward Plus renderer can adopt the various stages mentioned in this video. There are certain pre-processing steps that we need to take to make sure all content is pre-pass friendly, like reordering triangles, minimizing the amount of bits per vertex. The workflow should be dead simple checkmark actions that are final material slash artist needs aware, such as reducing the amount of bits based on object UV or vertex color requirements. The next two steps pre-pass semi-rare content that requires specific dedicated output buffers in the Basepass. By getting their motion vector slash MSAA data out of the way, while also enhancing our pre-pass depth, we comfortably keep our Basepass output count below the pixel shader limit. I feel more strongly about dual normal objects being motion vector pre-passed over emissives, because this setup prevents alpha tested content from having access to emissive properties. Since there's a surprising amount of sci-fi slash fantasy games that have emissive alpha testing, in that case the emissive buffer can just be included as one of the main Basepass outputs. It should even fit perfectly fine with the Basepass layout we suggest here too. Now, because we will have a pre-pass containing the best occluders, it would be nice to take advantage of that with some sort of occlusion approach that could minimize our Basepass draws, but I haven't found this to be a well-researched topic. Alright, as usual, a Basepass follows the pre-pass, but luckily all the core rendering technicalities were explained during the pre-pass segment, so discussing these steps should be pretty simple. Now that we don't pre-pass our close alpha-tested content and lose that depth surface area, we need to compensate by rendering all of the alpha-tested content that would appear in an alpha-tested partial pre-pass first in the Basepass. That test we did shows the additional depth provided by the removed draws in between the pre-pass and Basepass didn't affect the 13% performance boost in the lone Basepass draw via additional depth occlusion. Now the rest of our Basepass can depth test against a resource equivalent to an alpha-tested partial pre-pass without the performance cost. Then we need to render all the non-pre-passed, non-alpha tested geometry. That means all the content in this pass will suffer from overlap overdraw, where z-sorting isn't accurate. But this is fine because their small size makes the overlap too minimal to care about in comparison with the inherent quad overdraw this content will induce. And no, a visibility buffer would not be good here because we still have to face the quad overdraw, then compute even further to evaluate the material. But after this step is done, the draws together provide a massive amount of depth surface area. This will help the GPU render the remaining alpha tested content, since this content will still incur a much more problematic overlap cost that will massively benefit from full scene depth testing. The last steps just render the pre-passed content with the appropriate render target outputs. Some upcoming content will show how beneficial the proposed approach here would have been had such product used it. Now the meat of what the Basepass discussion requires is why certain decisions are made, what needs to already exist in terms of research, and what workflow this caters towards. 32-bit depth was chosen because of some AMD hardware quirks, and it is the highest quality output typically used for large environments. This should be using reverse Z rendering. NVIDIA has an article on it, just search NVIDIA reverse Z rendering and you'll find it. The Callisto protocol gets amazing results using 10-bit normals, so I don't feel like risking a drop in quality using 24-bit normals. But at least we know we don't need RG16 normals, which some games use. An RGB10A2 allows us to easily store an anisotropy flag and one lighting channel stencil in the last 2 bits, which is really important for keeping characters looking acceptable in modern games. The G-buffer layout is largely undecided as of now. Storing albedo and roughness together might be helpful for rain effects, as both of these pertain to porosity effects. But this is more of a reference to Need for Speed 2015's G-buffer layout, since the Caustic SSR uses an albedo roughness RGBA8 to determine scene variance. I do appreciate some aspects of the UE4 layout since it provides an isotropy, metal, specular, transforms the opacity channel into a cloth value via shading model ID, but this pipeline may not have to pack eye or hair data, and a lot of per pixel approaches in UE aren't really needed with the workflow we propose. In many games there are so many shading limitations in terms of throughput, outdated photographically validated parameters, and limits on how many objects can express natural shading. This is why we're proposing a new workflow that aims to rework the common metallic and specular PBR channels. Take this painted material with iron weathering. Paint tends to have specific BRDF properties, and even if the lighting shader fetches a material profile with paint-like BRDF expressions, our metallic buffer's function becomes too shallow as it tries to blend metallic values to portray thinning paint. Metals have their own complex expressions, and changing values in the ID map won't blend the iron metal values. It will just completely swap out the lighting appearance. This is why the ID channel must become a dual material profile ID channel that sends the lighting shader to fetch a pre-created dual profile. The previous metallic channel now determines what profile is predominantly expressed in the shading process. As long as artists don't create too many metal variants for blending, the production shouldn't hit the 8,000 slot limit. Remember, if an artist needs an additional metal like gold, the artist can just change the ID of a pixel to another material profile with a gold variant and bias the metallic blending buffer completely. Artists only need to create metallic variants if they need blending, which doesn't need to be that common. The specular PBR channel needs to be reworked as well, as it tends to represent index of refraction data, which doesn't fit in the typical 8-bit allocation. We can store a higher precision index of refraction variable in the material profile and have the specular channel always scale that value to 0. This means the legacy specular/cavity maps will need to be pre-processed so that edges between the material profiles are always the closest in value. That is, unless we find a way to completely replace cavity maps with the baked bent normals. As a quick reminder, the DMP ID channel is separate from the shading model ID, as we'll explore the difference later. I've seen many people ask things like, what's the proper poly count range for foliage or certain assets? A very freeing philosophy for artists is to know it's not a matter of poly count, it's a matter of overlap and quad overdraw. This is what artists have to manage in very specific ways we've covered in previous videos. Now let's review some of the workflow notes. Unreal Engine provides partial pre-passing and a quad overdraw debug view mode based on the post-Splinter Cell conviction development, but it doesn't display overlap based on what objects haven't been previously pre-passed. LOD transitions should only be using an ALU-based 2-position jittered Bayer matrix. The arithmetics it requires is going to be nothing on modern hardware. and Days Gone's LED transitions really blew Decima Engine out of the water. Also, make sure that the retrospective shadow map draws are dithered, since that destroyed KCD2 with popping issues. The specular aliasing is mentioned here because multi-billion-dollar engines like Unreal are still using the oldest anti-specular shaders from Valve, in which several developers since then have created improved versions. We will utilize SV coverage, a hardware feature that tracks our scene multi-sampling coverage. Multi-sample rasterization and sample frequency shading act as cost multipliers to scene quad overdraw. This is why Crysis 3 didn't use SV coverage, and instead used a fake coverage mask derived from the depth and normal information. But we proved that their approach removed too many multi-sampling coverage points, creating a basically worthless MSAA coverage mask. This is why we need to bake information into the vertices that are aware of shared flat discontinuities, which can potentially use a small amount of bits reserved for vertex colors. The vertices for this edge will not be affected, because bent edges between triangles need multisampling, as do lone triangle edges. So our SV coverage mask should look a bit like this. Obviously, we need to develop the appropriate shaders and baking tools, but this should be a massive win for deferred MSAA, because in forward rendering all these flat mesh discontinuities would be forced to process redundant lighting evaluations. Anyways, there are a lot of cool ways to promote these kinds of optimizations. We could discuss more things like building upon pre-existing quad-friendly retriangulation algorithms, why most environmental PBR assets could be converted into tiled mask materials instead of the typical memory-hungry triple uniform layout, something we talked about in our Callisto Protocol pipeline analysis. But our engineering followers will just have to brainstorm on these workflows alone for today, since we want to focus on explaining the pipeline in this video first. Alright, so the next steps are pretty simple. This large stage is modeled after two major pipelines, the first pipeline being the G-buffer resolve stage that takes place after Crysis 3's Basepass, where multi-sample zero data is stored in non-multi-sampled render targets, and the pixel frequency MSAA stencil is created. Then, the MSAA stencil is written inside the hardware depth stencil channel for later stages. As of now, we are not going to use or generate non-multi-sampled G-buffer render targets, simply because I know our target hardware isn't going to be affected by the bandwidth, and we're going to create a sample frequency stencil, which will help the hardware access multi-sampled render targets more efficiently. Our sample frequency stencil data will also contain bits representing that sample's shading model, which is where we start to resemble techniques used in Days Gone, in which after its base pass, first combines the 24-bit hardware depth with the 12-bit displacement channel just before decal projections. Then another step is taken to combine the decal buffers with the new bit-shifted render target outputs. But our pipeline doesn't suggest decal buffers, so this step is avoided. Basically, this first step stores either the 32 displaced depth or 44-bit channel data in our overwritten/upcoming specular lighting 2x MSAA RGBA 16. While the SV coverage related data and shading model bits are stored in either the remaining RGBA 16 or separate 2x MSAA 16-bit depth buffer, so that our next step can write all the information into our hardware depth stencil buffer. Empty/disabled subsample values and sky pixels will share a stencil value in the hardware stencil channel. It's probably best to generate other resources needed for later stages afterwards. After that, occlusion queries can be done with precision and ease. Baked lighting-bound workflows based on the Callisto Protocol development must be implemented in the engine, and decal buffers need to be avoided, since those will require unperformant resolve steps and memory we can't spare. Decals in Fox Engine write to all the render target channels except for the shading model ID. This means decals take on the shading properties of the base object, but adding a workflow that allows artists to generate an opaque threshold for overriding the material expression ID should probably exist. It's now time to discuss how to render non-cascaded shadow maps, which render scene depth from the perspective of the retrospective light to provide shadowing information. There's a lot of research that needs to be completed first, such as finding out how beneficial MSAA shadow maps can be, what precision our shadow maps should be using, but those aspects have to be tested after two major requisites are implemented first, such as perspective shadow map logic. Even though shadow maps only usually render cheap depth information, many shadow maps per frame need to be rendered, so every little shading and surface area is a big deal. I cannot stand seeing games render massive amounts of depth in areas where the on-screen light can't logically evaluate that shadowing. And these images are previous examples shown on the channel regarding this issue. But let's look at a dedicated example. A shadow map is projected on the scene by cross-referencing the shadow map depth and the player's scene depth. But sometimes we can get artifacts like light leaking and jagged aliasing issues, which sort of put into perspective how low resolution said object's representation is inside the shadow map. Now, every mainstream game or engine gives you the option to increase the shadow map resolution with higher settings. And while high-resolution shadow maps can mitigate the previous issues, or maybe even solve them completely, which by the way almost never happens, the biggest issue is the massive 4x or even 8x increase in depth surface area shading, which causes our performance to plummet, when we could instead use the player and light's view positions to render the shadow map closer within those bounds, and scale the shadow's field of view based on the player's perspective. By scaling the shadow field of view, we can see that this pawn's shadow map representation is being rendered at a much higher density. Therefore, when projected, we have far less jagged aliasing. This is perspective shadow maps, and even though this paper is more than 2 decades old, it was honestly ahead of its time, because the downsides are either irrelevant on modern hardware or largely solved with new algorithms. Processing power that can handle the cost of the 1080p plus 8% rule we discovered in our analysis of Days Gone. It's a depth rendering density that the shadow resolutions need to constantly scale for while remaining under a 2048 squared resolution, as anything above this is too wasteful and expensive. The shadow map size should begin to shrink as it becomes more distant within the frustum of the player's camera view. I'm not going to go through the workflow notes, since those are pretty dead simple to understand. Next up is the deferred rendering. Every time we find a game that uses compute shaders to process all lights in one draw, the singular light per pixel cost has always been slower than stencil volume lighting. Stencil volume lighting is used in Fox Engine, Crysis 3, and Days Gone. It's when an extremely cheap geometry volume representing our light is rendered inside the stencil channel to increase pre-existing values within its retrospective light's evaluation range. This way, expensive lighting shader pixel invocations don't waste time on surface area where the light can't even affect those pixels. When the lighting shader is specified to only invoke pixels for stencil values created by the stencil volume, we save invocations, therefore cost, and the lighting draw simultaneously reverts the stencil volume values to what they were before. Fox Engine uses the same geometry for both the stencil volume and lighting draw, but this will induce unneeded quad overdraw in the mesh discontinuities, when the lighting shader could just draw a single full screen triangle instead, as this is what Days Gone does. Except Days Gone draws multiple full screen draws for each shading model. While quad overdraw will be induced along each shading model edge, this is far less problematic than the alternatives, which is why our pipeline has adopted this approach. By separating each shading model with a different draw, we can load a different material expression ID, as each will hold different values, and we can selectively optimize bandwidth requirements per pixel. For example, the skin shading draw is the only shading model that should be sampling the dual normal buffer as input, similar to how skin draws in Days Gone are the only shaders that use the custom skin shading lookup table as input. While related to some important topics I think our developer following should look into, separating the shading models creates complexity room for advanced PCF anti-alias shadow map projection and more complex BRDS/shading models. In comparison with, say, UE's approach that has so many branches for different shading models, it has to separate shadowing in a slower separated pass from lighting, along with so many other issues we've talked about previously. Because of our perspective shadow maps and discoveries regarding how destructive shadow softening can be, these aspects should not be toggleable or accessible on the artist's side. Artists will have to remain restricted to barely softened shadows for perfect biasing. Out of the options that artists have right now, this is the best choice hands down. Shadow leaking and shadowing biasing is an area this generation of graphics needs to solve already. Maybe the next generation can dominate shadow softening since the required higher resolution shadow maps and advanced/more expensive shadow softening logic will be computationally affordable. Do note that the timing here is under the assumption of high action content, and the lighting shaders need to draw a permutation at a certain distance that swaps out the shadow map projection with noiseless/high sample count screen space shadows. I want to mention the fact that stencil volumes become slower with MSAA depth stencil buffers, which is why the volume itself needs to be rendered with early stencil testing to prevent invocations on subsample pixels where that empty/sky shared value is currently set. Sun/moon shadows are a bit trickier since they usually use cascaded shadows, which render several shadows from the same perspective with progressively decreasing distances from the player's camera to shadow large-scale worlds. Perspective shadow maps were originally designed to enhance sun shadows, but more testing would have to prove better results than orthographic shadows using proper distance ratios, which is referenced here from Days Gone. Far-field cascaded shadows, which typically shadow content beyond 3 standard cascades, don't need a whole lot of accuracy, but it's still a work in progress as Dead Space Remake and Days Gone have their own approaches. But it turns out KCD2 uses 5 cascades per frame, but updates the further cascades across a few frames. I'm open to this approach, but logic needs to exist for culling objects that can't logically cast into the player's view to reduce surface area shading. This is an issue that exists for non-cascaded shadows, but perspective shadow maps inherently relieve issues related to this. It also needs testing with high-speed movement like you'd find in racing scenarios and frequently camera-cutting content, since these scenarios can cause 2 cascades to be totally invalidated. We could potentially compensate for camera cutting by rendering those last cascades in the same starting frame at a smaller resolution, then have those scale back to the original 3-frame alternation. Overall though, it just makes sense to rely on approximated distance shadowing, such as the Atlas system used for foliage and Days Gone, or sign distance field shadows with native resolution projection. Remember that Crysis 3's 6 cascades cost around 1.2 milliseconds, but we're aiming for half that cost. And the biggest performance killers in that scenario came from the last cascades where static high poly or alpha tested content was drawn, both of which approximated shadowing techniques could help with in terms of performance. Shadows need to be pre-reprojected on a native resolution 8-bit buffer channel to make blending various techniques easier. We'll save some performance by using tricks used in Crysis 3 that utilize sample frequency shadow masking. The workflow notes are pretty basic, but overall this is just an incomplete area in terms of research, and I think there's way too much potential we're throwing out with costly alpha-tested distance shadowing that could be handled with approximated shadowing and further cascades. Now when you advertise about shadow optimizations, you should focus on your results being noiseless, artifact-free, and faster than ray trace shadows. Remember that new games lack so much shadowing in comparison with titles made within the last decade because of unoptimized geometry, no approximated distance shadowing, and bad practices such as shadowing floors. Shadows are not expensive if you properly optimize them. If you focus on fixing these issues, you should have a lot to work with in marketing material. These next stages are mostly a work in progress, and somewhat optional if we want to reduce the amount of shading models our lights have to iterate through. Eyes and hair should either be forward rendered or tile deferred shaded, since these materials don't generally consume much screen space surface area. These should be using stencil testing from values written during their Basepass draws. Remember that forward rendering doesn't exclusively mean lighting. For many years, it's just a way to reference that mesh rendering is used for geometric context a full-screen pixel shader can't provide, such as the Subsurface scattering pass that forward renders related skin textures that couldn't fit inside the G-buffers on the diffuse and specular resolved lighting, which is forward rendered again, meaning the same head mesh is used to render that result with even more skin textures and specular input. Since many games, like Days Gone and Callisto Protocol, already forward render eye meshes, there might be some benefit in merging some of the work. Hair is more of a work in progress, but the end result should be catapulted thanks to MSAA. The core discussion here really concerns eyes. I've seen many people mention experimental eye shaders that cost several milliseconds, and that's not what we're aiming for here. Both Days Gone and the Callisto Protocol forward render additional eye layers that cost under 0.2 milliseconds in the translucent pass in addition to UI's eye shader model. We simply need to implement more special attributes like tear lines, brightness adapting pupils, and features explored by Striking Distance Studios such as internal pupil flares as they were coined and internal iris shadowing, which was locked to RT shadows. These attributes are incredibly important to crossing the uncanny valley, and we should be able to achieve the results without RT, but it's going to require standardized workflows that can deliver the related eye shaders, live eyelid, and light position values. Information forward rendering already has to access. Now the next topic is global illumination, and since this area is pretty complex, and honestly not concrete enough as the approach could easily change with more research, I highly suggest reading through this section yourself. The basic core idea is that we'll determine global illumination / indirect lighting by tracing our shadow map information first, then falling back to a world space tracing method. Do not waste time implementing reflective shadow maps. These are low-resolution shadow maps with color and normal data, which are used to gather world space, meaning not limited to screen space, direct lighting information. This information is used to then propagate an approximate indirect lighting into the screen space view. Reflective shadow maps, or RSMs, cost around 0.3 to 0.6 milliseconds if you render them every frame. That's a lot in comparison with the zero cost of not rendering it at all, and instead feeding your indirect lighting evaluation process with the pre-existing shadow maps and baked world space information, as Days Gone and The Division do. If these layers are provided under a 2 millisecond budget with noiseless results, and your direct lighting will be massively complemented. Now, I already foresee some bad faith or ignorant discussion points regarding this topic, and some comments on this repost kind of perfectly encapsulated what I need to quickly address. This guy Ryan here was kind of mocking baked lighting in terms of large-scale worlds, but there's nothing to joke about or mock other than the fact that UE's only form of baked lighting is light maps. Light maps are a stupid technique for the majority of games, because they are the least robust in terms of interactability and memory. Several other games we've discussed on this channel, The Division, Days Gone, Fox Engine games, use baked grids or noiseless probes, which are much more memory efficient. They can look worse unless noiseless SSDO and SSGI and a separate large-scale occlusion system is put in place. Two systems that should not require massive storage requirements, which was one of the first points John Lindemann used to gaslight other users into thinking slow, smeary GI is acceptable. He repeats this stupid, outdated lie about static environments and dynamic objects appearing different because baked lighting so-called requires different lighting methods. Oh look, Alan Wake 2. Static and dynamic objects lit with the same sparse baked lighting grid. Days Gone. Static and dynamic objects lit with the same baked voxel GI and occlusion tech. The Phantom Pain. Oh look, static and dynamic objects lit with the same baked lighting probes. Stop listening to Digital Foundry. And the next thing is stop asking for worse game tech because you think it's going to help game devs. This was a lie propagated by marketing slaves and lazy studios that need to damage control. Outside of the fact that it's not practical to develop a game with noisy or slow visuals, a fully dynamic or even ray-traced version of the baked tech can reside in the editor to help artists iterate faster, and the shipping product can use a baked version based on the final artist results. This is not some ultra special solution that requires galaxy brain level thinking. It's common sense. This is already a workflow offered by DDGI. Stop letting productions like the one that made Doom the Dark Ages damage control through obvious ignorant morons like Digital Foundry. These influencers and these lying studios are Nvidia/Sony pimps, and they want to blame your hardware to distract from the fact that they are too poor at managing their development budgets or too lazy to develop a system that helps both consumer and artist needs, as described in this section's notes. Reflections are much like GI in the sense that it's a layer of systems that uses non-ray traced methods first to minimize world space tracing. The stages here are pretty self-explanatory, so I won't go through much of it, other than the fact that world space RT representation should be near voxel simplified, and dynamic cube maps are not entirely out of the question yet. Screen space subsurface scattering is the next area that needs a lot of testing and development work since we want something optimal for MSAA. Subsurface scattering is when we blur the diffuse aspect of our object to add in scattered translucent color. For instance, red is often chosen for skin. The Phantom Pain does this at native resolution with a pretty aggressive blur filter that is sort of destructive to shadowing. Newer methods are a lot more conservative with how much they affect lighting, such as this Callisto Protocol frame with full resolution RGBA16 subsurface scattering. This approach also references the subsurface profile ID of the pixel to look up its unique translucent color. Silent Hill 2 Remake by default shades subsurface scattering at a half resolution, and as you can see, skin details appear too blurred, and we're dealing with upscaling artifacts. Skin blurring isn't even the biggest issue, as an optimization I've only been able to find in Callisto Protocol uses a half resolution subsurface resource and only blends 80% of that half resolution result with the native resolution non-blur diffuse buffer in the following specular diffuse resolve stage to look near identical at 3 times the speed. But it doesn't help with upscaling artifacts, so unless we use an ID and depth aware upscale, I can't really recommend half resolution SSS shading. I like how Days Gone and Phantom Pain managed this effect in only 2 draws, but Days Gone uses the combined specular and diffuse lit result for SSS shading, and I feel that the result is questionable, and not particularly faster than native RGBA16 SSS in Callisto Protocol, when the RG11B10 input formats in Days Gone are forced as RGBA16 formats. This might be a good scalability option if hardware has issues with said RGBA16 diffuse buffers, but you might as well use a Crysis 3 alike method with stencil testing and a modernized gbuffer layout, which ends up being around 3 times faster than Callisto Protocol with forced RGBA16 inputs, and Crysis 3 is automatically outputting to an RGBA16. After some testing and comparisons with a singular light to isolate the subsurface scattering impact in the original Crysis 3, I find these results really impressive for its cost. It's a pixel shader implementation, meaning it can use stencil testing. I'm not finding any banding or noise, and all it really needs is access to an ID buffer to look up unique subsurface colors/properties. We can probably easily merge this pass with the next stage. So we can either aim for a 1.4 millisecond full screen cost modeled after Callisto Protocol's native RGBA16 UE subsample 2 compute shader performance, or look into something more conservative, since I think Callisto Protocol shows that there's actually too much subsurface scattering in which a lower and cheaper sample set may be appropriate. If you run into banding, use the same 2-position 2x2 jitter Bayer matrix and take advantage of 60 FPS persistence. Unreal Engine is one of the few engines that doesn't use normals for this pass, but I can't say they matter though, since the subsurface results in Callisto Protocol seem adequate. But overall, in general third-person gameplay, this should only cost around 0.3 milliseconds. Since these last few topics are such massive working progresses, I'll let these example posts explain some extra details, since it's best to explain these aspects in their marketing anyway. Alright, so the next step is combining the diffuse and specular lighting buffers. Now plenty of games don't have this step because they store the diffuse and specular result in a combined fashion. This separation is mainly done because of that screen space subsurface scattering we need to perform on the standalone diffuse result. We already discussed how Days Gone's customized UE approached that effect, but Epic Games' UE will checkerboard the diffuse and specular result if the lighting buffer is a 32-bit RG11B10, which works okay but causes similar issues as upscaling half-resolution screen space SSS. Besides these artifacts, I don't want to adopt this approach because I'm hesitant to settle for an RG11B10 lighting buffer, for reasons I'll come back to in a few moments. What we want is our lighting to be stored in an RGBA16 lighting buffer, and we want those results fed into the SDR or HDR tone mapping step. KCD2 in Dead Space Remake shades the majority of material lighting in a single RGBA16. But KCD2 uses an additional RG11B10 for skin diffuse, before compositing it with the main lighting buffer, which holds the specular skin result. But now, skin isn't being shaded with RGBA16 precision like the rest of the scene. Dead Space Remake fixes this by ensuring the secondary skin diffuse buffer is also an RGBA16. You can use an RGBA16 lighting buffer in Unreal by changing the scene color format value from 2 to 4. Which allows the entire scene to have RGBA16 lighting and uses the alpha channel to store data that helps extract the standalone non-checkerboarded full-resolution diffuse result for the screen space SSS pass. I don't want to adopt this method because I want to measure the error with the reference approach first. And we need the standalone skin specular result for a Gaussian blurring step mentioned and unfortunately poorly documented aspect in Striking Distance Studios' character rendering research. This is the only apparent reason why Callisto BRDF shaded objects in TCP would use a secondary specular buffer through custom engine modifications. Both formats respond accordingly to the scene color format command. Crysis 3 uses two RG11B10 formats for the diffuse and specular lighting buffers, then combines them with the base color data in an RGBA16, because according to Crytek, the extra precision isn't needed until material colors come into play. This is something that Alan Wake 2 could have taken advantage of, but didn't, at least during the time we did our analysis. They may have upgraded by then. But I want to verify Crytek's opinion on this matter on a better SDR and HDR monitor, specific content, and pipeline design first before adopting their advice on this. The main reason I feel very strongly about RGBA16 lighting is because the best looking games I've seen in terms of lighting contrast are games that use pure RGBA16 lighting, such as KCD2, Dead Space Remake, and The Phantom Pain. Maybe it's placebo or coincidence, but that's why we need more testing and validations. The Phantom Pain, unlike other engines here, tone map the lighting in the same draw where base color data is blended in. And while I think the benefits of this approach should be investigated, my main concern is compatibility with VFX compositing, as we're going to want to copy Crysis 3's approach for tone mapping for later anti-aliasing stages. Plus, we already have a viable 2x MSAA RGBA16 if we use full resolution screen space subsurface scattering. This pass tends to be a great place for functionality merging, and fog shading makes the most sense at this point. Maybe it won't be necessary, but both Need for Speed 2015 and the Phantom Pain use fog atlases from this point. But maybe an ALU approach might be better. After we get the direct lighting resolved properly, we need to compute the sky and cloud rendering as many other pipelines do at this point. Now, unlike other timings, if you add them up, they'll end up matching a 59 FPS cost, because this does assume high action worst case scenario rendering. But you shouldn't add this cloud timing without understanding its context. The per pixel cost of cloud rendering should scale with the Basepass surface area, which also scales with the cost of indirect and direct lighting. Even if you have an elaborate cloud system, as long as an equilibrium between the cost of those three aspects is maintained, clouds really shouldn't impact performance much. We were going to do a video on Horizon Forbidden West, but Nixie's ports are very unfriendly to debugging software. So far, we've only been able to measure KCD2's comparable results, which you can learn about in this video. This is what the timings on our pipeline graph mainly reference. But chances are, we're probably going to want to replicate the results found in this GT7 presentation, as it goes through a number of sky-related topics with heavy photographic validation. I cannot stress enough how incredible the sky rendering is in GT7, and this resource confirmed my long-standing concerns with how uncanny sky rendering tends to be. So really bank on this marketing-wise if you explore this research beyond what we can cover about it in this video. This stage is pretty basic. Transparent draws like glass are going to be rendered next. But just before that, we're going to render a variety of decal options ranging from basic blending, which will allow artists to create things like this makeshift shadow beneath this Need for Speed 2015 car, and forward lit decals, which is important for blood or soot effects. The biggest performance optimization we can use in this section is the Phantom Pain's half-resolution min-max depth effect rendering for low-frequency effects and sprites. The resources required for this step should be used for half-resolution subsurface scattering if that route or scalability is taken. This will massively reduce pixel shader invocations by rendering effects at a half resolution without common low-resolution depth discontinuities. The only reason why this may not have had such a widespread adoption is because fine particles cannot be shaded at a half resolution. The problem is having to clear the two half-resolution buffers in between native resolution VFX and half-resolution shading. But considering how expensive the most simple native resolution sprite effects can be, I can't see the alternatives costing more. Now all of these VFX and transparent draws / materials should be writing additional values in the alpha channel that represent a responsive mask. This responsive mask will reduce the amount of temporal anti-aliasing blending in later stages. This is easy to get from half-resolution effects because you can just recycle the blend mask in their alpha channels. I remember seeing people make posts about how the newer DLSS models will handle particles better, when so-called smarter AI is just more expensive AI, whereas the vendor-agnostic solution is just being neglected. As for previous implementations of this responsive mask, these still look bad because the TAA shader accumulates more than a single frame. So in the end, these are the two main aspects you should market. Depth of field and bloom need more work. Again, that is just a consequence of making this video early. I will say for now that the best implementations we haven't covered yet are all half resolution and composited in the next stage, that being tone mapping. But we want to process DOF after anti-aliasing, and we want to do anti-aliasing after tone mapping, so again, this needs refinement. Now, as said before, the next step will be tone mapping, which will convert our high precision lighting into a format that our display can show. Why we don't render lighting in a format our display can show in the first place is a discussion we're not going to go into, and this video does a pretty good job showing the benefits of high precision lighting if you want to learn more about that. To make things clear, our focus is on maximizing limited RGB SDR content, simply because maximizing baseline standards will help us all better understand what benefits full RGB and HDR provide. Now let's get you familiar with tone map curves, which map our high dynamic range lighting into a format typical SDR displays can show. We can do this in a perfectly linear fashion, but this doesn't look too good, which is why many different tone map curves have been developed over time. We've shown in previous videos how ACES tone mapping destroys images with detail destruction and inaccurate colors, but let's take Reinhardt for example. It can make the image look more natural than linear mapping, but the overall image ends up looking too washed out and dull. Now in the past, this channel has discussed the GT tone mapper with heavy praise, and I want to go a little more into why. The majority of this curve is linear. The developers of this tone mapper specifically said this helped convey realism, and that was backed by Callisto Protocol, which adopted the standalone GT curve. Other standout games in terms of perceptually accurate color management also use linear portions in their tone mappers to some degree. The Phantom Pain is memorable, but you can turn to post-2017 Frostbite games like Star Wars Battlefront 2 and Dead Space Remake that most likely utilize display mapping. We'll show examples of that in a few moments. The next thing that makes GT tone mapping so good is the contrast toe, which makes the darker parts of the image shift quicker to black. ACES tone mapping only has a slight contrast toe, but it's not as effective because it doesn't blend into linear midtones. The highlights or the bright parts of the image are compressed by the smooth shoulder at the top of the curve. This is all pretty easy to understand if you simply see these pieces work together. Here is the scene with completely linear tone mapping as the exposure raises. Watch what happens behind the white sphere and specular highlights as we add the smooth shoulder from, say, MGSV's tone mapping curve. It's starting to look a bit more natural, but let's lower the exposure to understand the contrast toe. In this case, the GT contrast toe. Before the contrast toe was added, it wasn't apparent how much gray was in the image, but we don't need our exposure all the way down to see the profound effects of the contrast toe. It makes the image richer and aligns with how we see content in real life according to the de Vries-Rose law. While the MGSV tone mapping curve doesn't have a contrast toe, the custom curve on screen with the contrast toe is more similar to the Phantom Pain's displayed results, according to some basic experiments. If you have watched our Fox Engine analysis, you would know it immediately resolves lighting in a 24-bit color space, which uses that linear smooth shoulder curve that doesn't include a contrast toe. After certain effects are rendered in that 24-bit space, the result is color graded with a LUT. That LUT produces another 24-bit image with raised highlights and lowered shadows, like a retrospective contrast toe. That's why so many materials, such as the asphalt, gain more perceivable detail and pop a bit more color-wise without looking oversaturated. This was easy to confirm, as we can simply take the source 24-bit image and lower the shadows manually. The less difference we see in our manual color grading means we're accurately describing what the LUT grading is doing. We conducted the same test in some night scenes and found nothing was really too different except a dark blue tone is configured in the LUT, which really isn't a discovery considering it was mentioned at GDC 2013. It is technical competence that plays such a massive role in this title's vivid presentation. Today, it is wrongfully simplified as better artistry. The Callisto Protocol implements the GT tone mapper with console command configuration, which allows us to better understand its impact on realism. The footage below is using the DX11 mode, so shadow resolution and cube maps butcher the graphics, but again, that is unrelated to tone mapping differences shown here. Hopefully YouTube compression won't destroy the differences shown here, because in person, The difference in SDR was massive. The contrast toe is removed by default in this title for unapparent reasons, and the smooth shoulder value is changed to compensate for an overall curve change caused by the contrast toe removal. It seems like they were trying to match the default smooth shoulder, in which a value of 0.527 would have been more accurate. The contrast toe command seemed to be the only custom command that had a decimal place shift, since a value of 0.22 completely overtook all mid-tone values, unlike standard implementations where a value of 0.022 will result in identical removal of the contrast toe. What you get with true GT tone mapping, the result that you see on the right, is deeper blacks, which makes you feel more like you're in the room with these characters. More detail is visible in some textures, and colors appear a little more vibrant without looking oversaturated, in comparison with other tone mappers like AGX Punchy, which compensate for the defaulted desaturated look of plain AGX. The impact of these tone map curves should make a lot more sense now, but there's another issue that needs discussion: hue shifts that distort material colors. This is a common issue even the GT tone mapper suffers from, and one of the main issues the GT7 tone mapper aimed to fix, not by removing, but by changing the behavior of the hue shifts, such as remaining more neutral color. As a quick reminder, the GT tone mapping curve is already less susceptible to color distortion in comparison with other tone mappers, like the ASUS curve. There have been previous attempts at preventing hue shifts, such as Frostbite's 2017 display mapping, but it doesn't have a contrast toe by default. This comparison is meant to show off the main differences in hue preservation and highlight compression. GT7 shifts towards white much faster in comparison with other tone mappers because when typical tone mappers hue shift, GT7 keeps that shift more neutral colored, as you can see in the red GT7 sphere as we decrease the exposure. It's a more neutral colored hue shift because the only neutral alternative to an orange hue twist is a white hue twist. The blue sphere doesn't transition to white as fast because its base color is a darker hue than the spheres above it. Display Mapper's transition to bright white is more uniform, but the main issue with display mapping is its inability to portray vivid colors as well as GT7 tone mapping when the exposure is set properly. The color on display is the orange sphere's material base color. Because the properly exposed result is priority, this is partly why I continue to strongly advocate for GT7 tone mapping. While you might point out that GT7 tone mapping still has hue shift in overexposed areas, this is actually more perceptually correct than display mapping, because display mapping shifts towards a more washed out appearance. The high exposure hue shifts in GT7 tone mapping was specifically kept to mimic camera footage, and because of this, GT7 tone mapping accidentally mapped accurate naked eye perception into display values. If you take a very vividly colored object, say an orange object, and decrease and increase the distance of a small flashlight against its surface in a completely dark room, you will find as the surface distance between the light decreases, the color becomes more vibrant. That is the opposite of the washout effect you see in display mapping. The most vibrant orange you can perceive is what the proper digital exposure represents. Because it's much harder for your eyes to be comparably overexposed, to force your eyes into being in an overexposed state, you have to lay a bright flashlight against the orange surface at such a small distance, the surface begins to match the blinding luminance of the light. Then, you will perceive what looks like a yellow hue shift that quickly transitions into blinding white. If you see a pure transition to white, you are most likely looking at a surface that is too smooth and is instead reflecting the white color of the light, but that would be digitally represented by the material shading, like an advanced BRDF, etc. So to map it out visually, our eyes provide a massive range of what you could call perfect exposure. That gray line at the end represents dark room adaptation, but that really isn't too relevant. A tone mapper correctly modeled after our eyes has to compress the adaptive naked eye range in a way that complements the structure of display values. As you can see here, the ratios need to be mapped out very differently because we want to use the full extent of our display power. If we increase the remaining RGB values by 50% at a synchronized rate, we will end up with washed out orange, like you would get with display mapping. Nowhere on our naked eye perception map do we ever see washed out orange as luminance increases. Now, when we did our analysis of Dead Space Remake, which most likely uses some form of display mapping, we didn't really get a chance to encounter a scene with lighting that wasn't flat, unlike this shot here. The lighting on the back of this character looks particularly excellent, but I do think the overall result is a little bit washed out and incorrect looking. Incorrect in rendering means uncanny. If you find the result pleasing, I simply think it's more of a testament to the importance of hue preservation and linear-like curve design. Now, as said before, nowhere on our naked eye perception map do we ever see washed out orange as luminance increases. But we do see blinding yellow, which is easy to shift towards as we progress towards white if we increase the remaining green values by 100% first. That is the behavior GT7 tone mapping matches so well. I'm not saying it's perfect, since we should look into how quickly we should transition to yellow, etc., and look into more advanced phenomenons like the HK effect and color desaturation that you can witness in absolute minimum lighting conditions. That one being a little bit harder to show on camera, but that will extend the representation of underexposed scenery with minimal blue values. Digital exposure, whether it's raw photography or digital rendering, acts almost like depth of field, except exposure acts as the depth of perception. And both depth of perception and depth of field need to be properly tuned so that our limited mediums, such as paper or displays, which are not perceptual mediums, look understandable to our eyes. That's why auto exposure is so important, and it's something this pipeline chart needs to document a bit better. The GT7 tone mapping presentation presents this great interconnected system that references tons of environmental values to calibrate auto exposure. And this is very important to implement because, as a player, this is going to help you get more artistic visuals in your game because artists are going to have their technical calibration side reduced, which helps the overall development, but will give artists actual time to produce unique visuals. The other important thing to implement is an automated white balance system, especially since hue-preserving tone mappers can appear a little more warm than usual. There are obvious technical reasons why we would want proper and consistent white balance, but it's also more accurate to our naked eye perception since our real eyes can adapt to different light temperatures without much issue. This will make a huge difference, and I think that's shown pretty well in this tunnel shot here. Now, you might say you want a colder look, or maybe you're using bright red lights in a horror scenario. We can implement things like a minimum and maximum auto-tuning range, and a scene temperature bias can be implemented for artists if that's really needed. We already implement these mechanics for auto exposure. Now, from this shot, it makes it look like they use the base color integrated lighting buffer instead of the diffuse lighting only buffer. This is important for reasons I'll explain in a few moments, but some might challenge me by pointing out a diffuse only buffer exists in this slide. There's a high likelihood that this is just a limited debug view mode instead of a readily available pipeline resource. The only thing that could potentially indicate that the GT7 engine provides a usable diffuse only lighting buffer without material color integration is this color output that might be blended in with both the separated diffuse and specular forward outputs. But back to the main topic. We want to utilize the diffuse only lighting buffer for reasons explained in this 2013 GDC presentation. I highly suggest watching the timestamp shown here since they use a video showcasing the real-world auto exposure failures that happen due to darker colored materials. Fox Engine titles retain extremely consistent exposure by downsampling the diffuse only buffer, which isn't tainted by dark material attributes or emissives. Adopting this might allow us to simplify the auto exposure / white balance pipeline while providing similar quality to the advanced GT7 system. But I do want to find a way to exclude emissives as Fox Engine does and ensure subsurface scattering, the non-screen space variant that takes place during direct lighting by using the opacity buffer, doesn't affect the auto white balance. Repurposing one of the lighting buffer RGBA16 alphas and ID system might be the best direction for that. As for ensuring tone mapping is performant, many pipelines will render information inside a small LUT, and then use that to accelerate the full screen tone mapping pass. Different games use different formats, but I'm a big fan of Callisto Protocol's 3D 64 pixel resolution RGBA16 LUT, since there are no apparent performance issues. but testing less precise formats for better visual to performance ratios can be easily put together in the future. Lastly, I want more focus on some LUT optimizations that sample non-linearly, which are implemented to reduce LUT banding artifacts. Overall, that's tone mapping for you. There are more things we need to look into, like changing the color space we render in, specifically BT 2020. Again, the results that team achieved are too phenomenal to ignore in terms of total adoption. The next step is anti-aliasing. The overall approach is mostly based on SMA-A4X and all the other things discussed in our Half-Life Alyx analysis, but with some modern touch-ups. Basically, you have to watch these two videos because they're going to show you why MSAA is important, why SMA-A4X is such a standout solution, etc. This video has already explained how so many different things in rendering work, but these use visuals and context that perfectly put anti-aliasing into perspective. Now, SMA-A4X runs after a pre-existing SMA-A S2X pass, which is basically just running SMA-A twice, once for each MSAA subsample layer. Now, the focus for this pass will be the morphological quality, or MLAA, as we will discuss the temporal aspects when we reach this part. To recap, we are not using MSAA to resolve jagged edges. We are using MSAA to supersample temporally unstable edges. So our basic jagged lines need to use a specialized solution via MLAA. This channel has already explained all the main MLAA options in the past, and have already shown several times that your standard TAA or temporal upscalers cannot resolve jagged edges better than MLAA. Lots of evidence on this channel has already been shown as to why SMAA is the only viable morphological option, and I'll be showing more stuff that makes that conclusion much more concrete. The original Crysis 3 provides the most competent SMAA, so it will act as our reference for now. Now, in the worst case scenario as triggered by this grass, SMAA S2X can climb up to almost a full millisecond cost because of how many lines and edges it has to blend. Typically, SMAA S2X is much cheaper as shown in this shot because most of the time large parts of the screen don't trigger SMAA's edge detection. That's why the timing here is much lower. Grass and foliage hurt MLAA performance in general. But you see, while this pipeline chart documents a worst case scenario, it already allocated millisecond timings for the visual effect pass, and most visual effects reduce the amount of processing SMAA needs to handle. So even if you encounter this worst case scenario, you will obviously have the processing budget to handle it, since it cannot exist without you first underutilizing your visual effect budget. And then the other reason why this cost is quite small is because the creator of SMAA discussed several different performance optimizations that led to a 40% increase in SMAA's performance. Crysis 3 didn't even use the smallest possible buffer sizes for the edge calculation mask and lookup tables. There were no code samples for the performance optimizations, but many of them were just common sense, and the biggest performance optimizations simply took from pre-existing open-source code for Mini-Engine's FXAA implementation. But what I want to bring attention to are these visual optimizations that this paper includes. It fixed some of the biggest issues that only temporal subpixel jitter and MSAA would tackle, this being high contrast edges. As a quick reminder, this is not related to the issue of missing edge smoothing found in mainstream implementations like Nixie's PC ports, CryEngine 5, and UE5, where those are unable to catch edges in comparison with the reference implementation. We need to investigate what causes this because it unfairly gives SMAA a bad rap, and I have seen it push so many people to combine or stack different morphological solutions, which is insanely inefficient. I mean, honestly, look at the difference. This is a perfect summarization of Epic Games' incompetence. Did this happen because Epic is lazy, or because they're genuinely too stupid to match graphical quality from 13 years ago? Pick your poison. Choose Epic's excuse, because the multi-billion-dollar company can't be held back by both. But anyways, let's get back to the main topic. Even the original competent implementation could not detect these types of jagged edges because of contrast issues, which were explained and fixed in the presentation with sample code. It's a huge improvement that needs to be standardized, along with its improved line detection, which not only helps keep textures unaffected, therefore cleaner, this should reduce the amount of SMAA processing. And as for the final visual optimization, the handling of certain patterns are smoothed to help the temporal stability. The temporal stability of the spatial component, mind you, not the temporal variant. In the past, we've complemented CMAA's minimal image impact, but even if a third iteration of CMAA with diagonal edge support is released, it will still be so behind what we know is possible through a fully modernized SMAA. Now let's discuss the temporal component. Now there's a lot of different implementations of TAA, and explaining why all of the few good ones are better has already been done on this channel within the span of 2 years. So what we'll do to speed up this chapter is explain why one of the best TAA implementations looks so much better than most, and explain how and what modern innovations/attributes included in this pipeline can solve its remaining issues. The standout anti-aliasing in question being SMAA4X, in which its temporal component is really just based on SMAA T2X. So let's cover why this is ahead of most TAA solutions. The first thing that makes this technique such a standout is that it only blends the current frame with the previous frame, namely the SMAA output generated in the last frame. It specifically does not blend with the last frame's temporal output, because that would cause the output to be muddled with outdated information, whereas two-frame blending ensures only the most relevant information is used for temporal blending. The majority of modern temporal techniques blend the current frame with an accumulation buffer, which is simply the output of the last frame's temporally blended output. So it's blending the current frame with an infinite amount of data, or an infinite amount of history, until a camera cut or until something vastly different in the frame triggers a history rejection, where it resets the pixel with the current frame information. The whole point of this is to achieve more samples within a pixel like MSAA without multi-sampling, by changing the center sample locations as frames are generated, which is just jittering the camera in sub-pixel positions. As the camera jitters, the TAA accumulation smooths the flicker. This is supposed to resemble MSAA. But the problem with this is that it falls apart in motion, causing smudging, blur, ghosting as we can see around both sides of this character. Another problem is that the jittered positions make it impossible to consistently sample edges for proper smoothing, as seen here with DLAA. The latest vendor-agnostic solutions like UE5.8 TSR on low to high scalability suffers from either flicker, severe blur during basic motion, terrible ghosting in the form of ringing as you can see appearing as a halo around this barrel, and you can only mitigate these issues by increasing the accumulation buffer size by 4x, which will demand a massive 2.2 millisecond cost, which is more than 18 times more expensive than the temporal reprojection logic used for the original temporal SMAA. All these ghosting issues persisting in new games is because of this accumulation buffer. These ghosting trails, artifacts, and general mass blurring is impossible to encounter when you only blend the previous frame, especially at 60 FPS, where the difference between such frames are very small. With two-frame blending, it jitters the camera to achieve the 2x MSAA pattern every even and odd frame. 2x MSAA will provide the same sampling as 2x supersampling, so after that foundation is achieved, it lets the morphological component handle the rest. Now, if you have ever encountered very blurry SMAA T2X or SMAA 4X, that is because those games, like the Crysis Remastered series and KCD2, are using the last frame's temporally resolved output as an accumulation buffer. Finding a true implementation of this two-frame blending is extremely difficult, and the newest implementation of semi-correct temporal SMAA is the SMAA 2TX and the PC port of Ghost of Tsushima. I say semi-correct because the morphological component fails to match the reference demo quality, but otherwise the temporal component is very clean, and has no ghosting whatsoever at 60 FPS. The original Decima Engine TAA only blended 2 frames as well as some early UE4 mobile TAA, but those have some other issues that introduce ghosting, but neither one suffer from major smudging or long ghosting trails like those other games shown before. The other positive aspect about the original temporal SMAA component was the narrow resolve, which I can explain using the still SMAA T2X frame. Still comparisons for temporal AA are generally worthless, but using a still for this topic will allow you to understand the core blending behavior. Now let's look at this frame before the temporal resolved kicked in. I know the ghosting looks bad on the grass, but we'll get to that later. What we want to analyze are some geometric edges that SMAA wasn't able to catch. Now, to refresh you, without MSA or TAA, every pixel has a sample point in the center, and if a triangle overlaps it, it gets rendered on screen. MSA8 will increase the sample count to produce a gradient which gives our eyes context about the scene density without any increase in pixel count. In the case that a triangle overlaps all the multi-sample points, the GPU will instead render one sample at the center, like no AA, which saves performance and helps textures remain completely sharp and unaffected. This should help you understand how these gradients are formed from these increasingly more complex sample counts. In the context of SMAA4X, it's jittering the 2x MSAA pattern to achieve a 4x MSAA-like pattern. We want that pattern because it provides sufficient density context before we encounter diminishing returns seen in higher sample counts. Because it's jittering the whole sample layout, that means when a triangle overlaps a pair of samples, the default sample location will shift in one of these areas instead of the center. But let's get back to the non-multisampled scenario. SMAA2TX jitters the center of all pixels, meaning it affects textures too, but that's an issue we'll talk about later. It jitters the center of all pixels in the pattern of 2x MSAA. So you should know exactly what the result should look like. It should be a basic two-step gradient. With the original SMAA temporal resolve, that is exactly what you get, a two-step gradient that resembles the reference of what we're trying to achieve at a lower cost. Many engines, like UE for instance, use something called a wide resolve. And this is easy to show since UE allows you to change the camera jittering pattern. So in this case, we'll use the 2x MSAA pattern. This two-step gradient is what you'd expect from UE's TAA. But this is not what you get unless you turn the r.temporalAA filter size command down from 1 to 0.09. By default, UE uses a hideous wide resolve, and not only does it blur up the edges into something your brain can't fully understand, it is super destructive to texture detail. Just take a look at the floor and china vase texture. At this point, your conscious mind is trained, and you don't really need the labels anymore since you can tell which one is which. So combine the wide filter with an already blurry accumulation buffer, and well, you end up with your typical Unreal Engine slop. The wide resolve is mainly used to so-called enhance the accumulation buffer, and attempts to solve issues morphological anti-aliasing can fix 1,000 times better in a single frame. This is almost comedic because UE's TAA presentation flaunted this very aspect. I cannot say this enough. Unreal's TAA by Brian Karras is an absolute failure at what it tries to achieve. It's based on false information and it's highly hypocritical as it constantly throws around the word temporal stability while pretending major blur and ghosting isn't a form of instability. Now I would like to show one more title that sorta enhances the reasoning to use a narrow resolve instead of a wide resolve. This being Days Gone, which apparently uses a completely custom TAA implementation, and luckily allows the use of UE's legacy 2x MSAA pattern with certain console commands. Now this TAA in motion is extremely poor because it uses an accumulation buffer and its rejection logic isn't strict enough. But we've previously complimented its still image for matching the late CNN DLAA resolve, as the difference between both solutions is extremely small to the point where it's highly possible both solutions were based on the same code. We just haven't traced it back to the source yet. But anyways, it turns out it's using a narrow resolve. This is easy to see as we zoom in on some edges. Now you might say this resolve up close looks a little odd, as if it's maybe not a totally narrow resolve. Well, it is a narrow resolve, but the odd aspect you may have noticed comes from a slight sharpening effect put on the temporal output/accumulation buffer, as we can clearly detect on the first TAA frame. Discovering this sharpening filter was an interesting bonus find, because it's typically very noticeable when sharpening is added to TAA, but this might be a good showcase of the viability for a slight sharpening option. Though the open source NIS upscaler from NVIDIA manages to get results that don't halo if you ever consider adding a sharpening slider in your title. But you would want to merge that sharpening with the TAA pass as seen here. Okay, so two-frame blending and a narrow resolve act as our main replicatable benefits of SMAA4X. Now let's talk about the issues of SMAA4X/T2X. Particle and visual effect ghosting. This happens because these objects have no motion information that inform the TAA shader to reject or reproject their pixels, which at 60 FPS isn't visible on a whole lot of screens because the ghosting effect resets every 16 milliseconds. But we still want to fix this issue. This problem was present on the comparison shown earlier too. We already discussed the solution to this, that being the responsive masks produced by visual effects. All that requires is an artist to flag the effect materials with the responsive mask option, just as artists are required to in many modern engines. The next issue was the ghosting present on foliage. If you're having issues seeing the ghosting, take a look at this frame before and after the temporal resolve. Yeah, it's pretty rough. This is not surprising though, because the foliage does not render motion vectors unlike animated characters. The temporal logic here uses something called velocity weighting, which uses motion vectors to determine how much a past frame pixel should be blended with the current frame. And as you can see here, only the animated hand and gun output motion vectors, which provide information about where that pixel was in the last frame. The lack of motion vectors for moving foliage was due to a 7th gen limitation that 8th gen easily overcame. Do not listen to people like this, the senior programmer of Path of Exile 2, who go around lying about the cost of motion vectors when we have shown in previous videos that motion vectors can be provided at a near free cost if produced in the Basepass. Now, as we were discussing, modern engines can easily produce accurate motion vectors for alpha-tested content, like foliage. But newer, mainstream TAA implementations don't use velocity weighting. They use color clamping instead, which only determines the blend weight based on color information, which has some benefits but is clearly not good enough. In fact, Filmic SMA had to utilize the current and previous frame depth to remove basic ghosting artifacts. But back to UI's basic color clamping, this TAA still uses motion vectors, but only for reprojecting pixels of the last frame. Mind you, Brian Karras specifically rejected the use of velocity weighting because it wouldn't help with the rejection of animated materials, which was an issue he introduced by insisting the use of an infinite blending history. This is a custom demonstration of UI's color clamping combined with 13-year-old velocity clamping. It still looks bad because it's blending an infinite amount of frames, but even then you can still pick up on a pretty big difference, especially in these areas. Now if we lower the frame accumulation bias a bit, we end up with way less ghosting at half the frame rate as Crysis 3's SMA A4X. So disregard 120 FPS plus narratives pushed by Digital Foundry designed to have you compensate with hardware you don't need. At the basic standard of 60 FPS, we can get some pretty good results even when an infinite accumulation buffer is used like it is here. Now honestly, we already know the ghosting can be fixed because I just showed the PC port of Ghost of Tsushima, in which full scene motion vectors had to be implemented by Nixies to ensure all the upscalers and frame generation worked as intended. So now you know. Responsive mask for preventing visual effect ghosting, and color clamped enhanced velocity weighting to prevent opaque object ghosting via proper, modern motion vectors. Now let's talk about the last issue we need to overcome, which tends to exist in almost every single temporal implementation, this being texture blurring. Now, we had focused on how much more clear the narrow resolve was in comparison with the wide resolve, but when it comes to texture detail, even the narrow resolve can't match no AA texture quality, which is the same as MSAA texture quality. Because temporal subpixel sampling is done on all pixels, unlike MSAA where it only subpixel samples edges, temporal sampling oversamples textures. Now, there's a bunch of so-called solutions out there, but obviously they don't work. One approach that's typically never utilized in games is jittering the textures in a synchronized fashion with the camera jittering, as documented as an automated feature handled in the Basepass. But as a last precaution to ensure textures are never affected, we can take a page out of the TS-CMAA code, which is a lot more than just being a so-called CMAA version of SMA2TX. Unfortunately, Intel has scrubbed all traces of this technique off the internet, and nobody thought to preserve the source code download link on the Wayback Machine, so showing off its advantages aren't too easy. Luckily, Final Fantasy XIV Online implemented TS-CMAA with CMAA2 code, in which we were able to capture for analysis. We're going to show what we found in this video since we're not going to do a full analysis due to this title not being a use case scenario we focus on. The green line overlays the transition from post-CMAA2 frame to the temporally blended frame. Now it doesn't use velocity weighting, I'm not sure how wide the resolve is, and it does blend with an infinite temporal history, but the majority of textures retain their detail because the blending only happens where CMAA detected edges. Here we have some solid patches because it reuses some information from the sun shadow mask, but you can see how much texture area was not affected by the temporal blending. We can easily adopt this logic with SMAA's edge mask, but we have something better, the custom MSAA mask saved in our motion vector buffer. So texture jittering in combination with that isolated temporal edge blending should keep our image quality 99% comparable to 4x MSAA. By the way, that TS-CMAA reprojection pass is crazy unoptimized as it uses the fattest possible formats as shown here, except as an experiment we changed the 32-bit motion vector RG16 to a 64-bit format to further stress how unoptimized Unreal's 28% slower 0.3 millisecond TA is. But there is another aspect we need to take care of if we want to match our temporal component with MSAA. We can jitter textures to rid the texture blur seen here, but that won't do anything for the subpixel shift in the lighting element as we can see in this ray traced shadow. I'm showing this ray traced shadow because it makes it easier to consciously recognize the issue, but your brain is going to subconsciously recognize something very wrong with the lighting and shading elements beneath the textures, especially when we're using very expressive shading models and BRDFs, etc. So in the end, we either need to find a way to offset our direct and indirect shading, or we might have to bite the bullet and subpixel offset the geometry with texture jittering compensation instead of jittering the camera. But we also have access to programmable sample locations. You see, SMAA 4X was designed to match 4X MSAA as much as possible since the original pattern is optimized for super sampling. But it's not totally accurate. If we use PSL programmable sample locations, we can match the 4X MSAA pattern perfectly, and the GPU will sample the center of the pixel if both samples are covered, which means we don't have to jitter any elements like textures or lighting. But the 4X MSAA pattern was made before morphological anti-aliasing was invented, and was designed to ensure quality edge gradients. We don't need that rotated 4-sample grid pattern because we rely on SMAA to take care of this. The developers of Decima Engine render 2 different subpixel positions every even and odd frame just like SMAA 2TX. Decima Engine renders the 2x MSAA pattern on the vertical and horizontal axis of each pixel center, so that neighboring pixels can provide 2 extra samples, effectively giving us 4 samples per pixel like 4x SSAA and 4x MSAA, but in a pattern optimized for thin detail. Using this pattern by programming our MSAA sample locations will look way better than anything offered in Decima Engine because we won't require any jittering or frame blending to achieve 4 samples. And textures will look way better since sampling non-edges so far from the pixel center hurts texture clarity. Here are the promotional templates to follow, and do note that the Luma edge detection with the lowered peripheral screen edge contrast should only be a scalability option, not the main option. Remember that this is an early look and eventually this will be updated, but I want to make a very clear reminder, any temporal logic should only enhance the existing MSAA edges, sort of like a colored CSAA. We might even want to store the last frames relevant to SV coverage data. But moving on, next up is motion blur. And really, this topic needs a dedicated video, but let's go ahead and explain how it's usually approached in modern engines and start from there. We're going to take a look at Days Gone for that. While this title does use a custom post-processing pipeline, it uses a motion blur approach that is honestly terrible looking. So this shot contains a capture that used console commands to re-enable the original UE4.11 default motion blur at its maximum potential quality. So in this pipeline, the motion blur pass starts a little before the tone mapping and auto exposure. And the first thing it does is combine the native animated object motion vectors and the native scene depth and reconstructs the velocity of every pixel using the camera movement values to make this native resolution velocity-packed RG11B10. That way the motion blur pass doesn't have to sample 2 resources, that being the depth and velocity buffer from before. In our case, since our depth and velocity are multi-sampled, making this resource, which will not be multi-sampled, will end up being a big help, and we can implement some special logic here. An optimization found here and in CryEngine 5 is that this 120 by 68 max tile RGBA16 is generated in the same draw. This is related to a technique introduced in this presentation, and it basically helps optimize the smoothing between motion blur edges as seen in this comparison. There are some issues with the approach, but we'll get to that topic in a moment. The small draw here dilates that max tile data as indicated by the inflated appearance, which again was standardized by that same presentation. We'll also show a comparison with and without this dilation step down the line. This pipeline needlessly clears the motion blur output. 7th gen games like Crysis 3 did not waste time doing this, they just overwrote the buffer. The actual motion blur draw simply uses the native resolution scene color, packed velocity RG11B10, and that dilated max tile resource to create the per pixel motion blurred result. Seeing the before and after sort of helps you understand what's really going on. But let's take a look at some well-defined lines to get a better understanding. You can see that it's basically repeating a pixel by a certain amount depending on its velocity direction. And these overlapping steps or gradients are why you see games implement noise patterns. Need for Speed 2015 used white noise, which is one of the better ones. Later versions of UE4 and now UE5 used interleaved gradient noise, which looks awful. Another awful pattern is blue noise sampling, which was used in Alan Wake 2, Wicked Engine I last checked, and Ghost of Tsushima. Those last two patterns are way more noticeable than this presentation's suggested approach, which is just a simple checkerboard pattern, which is what early UE4 used, as we can see here in Days Gone. Dead Space Remake and KCD2 apparently use this pattern too, as at the time of our Dead Space Remake analysis, we weren't 100% sure, but after some more investigating that got cleared up. We're going to discuss an alternative to this checkerboard pattern, but let's understand our chart a bit better. So here we have our velocity packing draw and our main motion blur draw. But why is the max tile velocity management missing / red coded in this chart? That's because that tiled resource is responsible for artifacts, and this shot does a good job showing that. Notice how there's a thick motion blur outline around the character. That's coming from the dilated max velocity tiles, and once you notice it, you can't unsee those massive blocky artifacts. Now, if we prevent the dilation, we can observe the outline becoming slimmer, and as a result, a little more natural. But those tiling shapes are still present, and the accuracy of some motion blur edges get messed up. This is another reason why I'm a fan of Need for Speed 2015's motion blur, because it doesn't suffer from these tiling issues because it doesn't use a tiled velocity resource. That's not to say it's perfectly plausible, as you can see it doing some odd stuff with these ran over debris, but then again, these don't output proper motion vectors. A good example of its implausible logic is visible on this barrel, where the road velocity behind the barrel smears on top of it instead of the barrel occluding the road velocity. Now maybe we can keep the tiled approach for motion blur, but we need a solution to this long-standing issue because it introduces an uncanny aspect that nobody's talking about or trying to solve. Now, there's something very specific we can do during the velocity packing stage, and really, it's pretty easy to understand just using some visuals. This is your typical post-2015 solution, which is called per pixel motion blur. You can see that the whole scene has motion blur applied as we turn the camera, which has pushed a lot of people to call this camera motion blur, which is not a good description because it makes it sound like it doesn't provide moving objects with dedicated velocity, which is the case here as indicated by the motion tile outline around the moving character when we're not moving the camera. Per object motion blur is the most demanded solution as of now, because it looks like it only smooths the animations. Really, it's just removing the camera movement from the velocity input. So in this case, camera velocity is being removed in the velocity packing stage. Moving objects in real life leave motion trails, but as we run, ride bikes, or drive, our peripheral view, or what we're not focusing on, becomes blurred. So what you're usually focusing on in a game is everything beyond 5 or 10 feet. And that's about the same for naked eye perception in general travel. So to match our naked eye perception, we should only allow camera motion blur up to a certain depth with decreasing intensity. This will allow your eyes to focus on distant content as you move the camera while retaining a natural sense of movement without the uncanny isolated look of per object motion blur. Now, a production implementation needs to use more of a U shape. This is just naively cutting off at a certain depth point. A low resolution mask will probably act as the best way to approach such a shape. And all depth beyond this point should be blurred under extreme camera motion because, again, you don't want to end up with an obvious cutoff. That covers how velocity packing should be handled, and this workflow note here simply documents the need for an exposed artist variable for changing the main camera motion blur cutoff. Now let's talk about the changes we need in the actual motion blurring pass. Take a look at this sample scene where some settings have been changed to make the issues with modern motion blur a bit more apparent. The character is going to run in the direction of this arrow, and what I want you to focus on is this white sphere, because if you analyze the movement of your own hand or velocity trailing in real life, it should only leave a trail in the same direction. Just in case you missed the issue, let's take a closer look. The problem here is that the object is actually centered in the blur. Even though it should have only left a trail in this direction, modern motion blur samples in the opposite direction as well. For years, this is the result graphic programmers have been aiming for because it resembles behavior you only see in camera footage. This same behavior was present in the Days Gone shot, and it's pretty uncanny. A game that only samples in the correct direction like our naked eye perception is Need for Speed 2015. Watch all the little lights in the distance stretch along the screen from a clear point of origin. Watch these single pixel car reflection speckles get these perfect micro velocity streaks. Now, if we take a look at these fire hydrants and overlay the original image, you might say it still looks like the motion blur makes them appear in the center. The problem here is that implausible velocity streaking from the background behind it, diluting their point of origin. This is actually similar as to why cameras have this issue and why our eyes don't. Single direction velocity trailing with plausible depth-aware motion blur is going to catapult graphics, but there's one more thing we need to ensure so that our motion blur pass is handled correctly. Despite the Phantom Pain's half-resolution, tiled artifact-ridden motion blur, there was always something about it that looked very pleasing and smooth. We're going to show why that is, since it was something we missed in our main Fox engine analysis. We're going to analyze this frame because its scene has better defined lines for motion blur analysis. And this was captured at 4K to ensure the half-resolution motion blur is forced to compute at 1080p, making it easier for us to compare these timings to, say, Days Gone's UE4 motion blur. Technically, the motion blur pass begins here as it downsamples and sorts the native resolution motion vectors into tiles. Note the cost, since this showcases the performance benefit of that merged pass via compute shader, as this pipeline was constructed before those became mainstream. This pass also doesn't dilate the motion vectors in the same way. It creates neighborhood tiles, which we won't get into for now. But the next pass combines the native resolution depth and the native resolution motion vectors with that 120 by 168 neighborhood tile resource inside a half-resolution, in this case 1080p, RGBA8. The RG channels pack velocity in a way that gives closer objects to the camera higher precision, and the BA channels contain the max neighborhood tiles in a bilinearly upscaled fashion. That means the motion blur pass only samples this resource and the scene color. We need to develop a plausible single direction motion blur before determining if we can adopt this optimization. The scene color resource used in the motion blur pass is downsampled from 4K to 1080p in this draw, which again is not something we'll adopt unless we really want a scalability option for motion blur. The next draw is when motion blur is actually processed, and this is where we need to take a closer look. This is not using single direction sampling like Need for Speed 2015, it's more like the Days Gone's motion blur we showed before. But what's interesting about this pass is that no pattern is being utilized. It's a uniform sampling pattern, and this pipeline smooths that uniform sampling pattern by running it in a separable pass, which simply uses the same velocity-packed resource input as before, and the uniformly motion blurred output as input to produce the final half-resolution output, which again is 1080p in this case. Now, in all fairness, the motion blur result is ultra smooth because it composites the half-resolution result to native resolution using bilinear filtering. And that will make a big difference if the input is going from 540p to 1080p, but when you're downsampling like here, that's not going to make a difference. Here's some downsampled footage that sort of gives you an idea of how this motion blur looks at our target resolution. The result here is so much more smooth because of that separable pass, in which most game engines throw in a noise pattern and call it a day. Now you might say you'd rather have a white noise or checkerboarded motion blur instead of a uniform plus separable pass motion blur, because you might not think it's as effective in ridding the sample iterations or those motion blur gradients. But the thing is, this motion blur only samples the original position 3 times per direction, whereas your so-called superior, noisy, or dithered solutions are simply sampling at a higher count, about 10 or 12 times every other pixel, to reduce the motion blur gradient. That creates a better baseline for the checkerboarded pattern, but it will also create a better baseline for a separable pass. Imagine how good this separable motion blur would look with a higher sample count. Well, you don't have to try too hard imagining, because UE offers a separable pass through a console command, since the concept has been around since 2008. This is what inspired the Fox Engine's motion blur, since Kojima clearly commissioned Fox Engine's development to resemble CryEngine, and Fox Engine's decrypted HSL files straight up copy this sample code. But you might be wondering why the sample steps aren't reduced as much in this UE example. This is simply because Unreal's separable pass is less competent. Here we can see the separable pass in Draw 9208 is almost half the cost of the motion blur pass, whereas in Fox Engine the motion blur pass itself, that being Draw 5717, is less expensive, which makes sense considering it's utilizing less samples, but notice how the separable pass in Draw 1718 basically costs the same as the previous motion blur pass, and is 40% more expensive than UE's separable pass. Remember that cheaper does not mean more optimized if it looks worse. The point here is that UE's separable motion blur is sort of make-believe, and it only got more worthless when Epic Games introduced interleaved gradient noise, which ended up staying in UE5. So what we want is a competent, aggressive separable pass that builds off of Crytek's sample code, and iterating on it with a few optimizations like in Fox Engine's case. The big question R&D will answer is how many motion blur samples do we really need now that we're using a competent separable pass? And do we want to maybe experiment with a checkerboard sampling pattern to get even smoother results? But chances are you'll want to use uniform sampling to prevent any chance of noise. Now another thing R&D will help us determine is the length of velocity trails. The closest digital term we've been using in the industry is shutter speed, but we need a constant value that matches our perception. For instance, the medium motion blur setting in the Phantom Pain is much more believable, whereas the sample footage we showed all used the high motion blur setting. We're going to have to find a proper result by comparing a digital hand on screen linked to a real hand with a motion capture glove attached. I'm not going to go into why the term velocity compensation is used here, but long story short, I think it's a more accurate term that describes what a monitor can't send to our eyes. It doesn't matter if your content is at 30 or 500 frames per second. Velocity trailing has to be simulated properly for a natural looking result. Again, this topic needs a dedicated video. There are common effects that utilize velocity data, like the swirling effect, but we need to do some more analyzations to document an optimal approach. Bloom is another topic that just needs more work. You can do it post-tone mapping if you store your scene luminance, as that's what the Fox engine does, but we might want to do something a bit more robust, since we want bloom that reacts to the motion blurred result. That's super important because it matches naked eye perception and can make a big difference in quick moving shiny objects like metallic weapons or spinning car wheels. Take some notes on how to market this, and let's move on to the last segment. Next up are composite effects and the UI. After 2020 and mass adoption of UE4, composite effects like certain flares and light source blooming sorta went away, so this documents an implementation using half-resolution compositing buffers. Even in very complicated scenarios, these can be processed pretty fast as long as a half-resolution buffer is used, like here in Fox Engine. You have to use a half-resolution buffer, or else you'll end up like Crysis 3, which uses a native resolution composite buffer, which completely chokes performance for pretty much no noticeable gain in quality. By using a half-resolution buffer, you cut pixel shader invocations down by the millions and make it harder for artists to hurt performance with over-the-top effects. Need for Speed 2015 is another title that takes advantage of a half-resolution compositing stage but it uses a high dynamic range buffer, specifically an RG11B10, but our pipeline has readily available half-resolution RGBA16s. Note, this pass uses a half-resolution hardware depth resource for depth testing, which is also the case for this half-resolution RGBA16, which holds rain and lens drop effects. That is composited on the frame later with bloom, so that those watery effects look like they're absorbing the local light. It's a very cool effect that this pipeline makes possible because bloom is composited in the same pass along with other camera effects like film grain, color grading, and chromatic aberration, effects we've gone over and discussed the proper uses for in terms of limited gameplay situations. It's too early to discuss in-depth UI rendering. The timing here is based on reasonable UI budgets we've measured in games before, and we'll cover more elaborate/demanding UIs soon. It makes sense to render the UI on another render target like some pipelines, for example Days Gone, because as we overlay that UI, we can apply gamma correction in the same draw. Callisto Protocol probably has the best gamma correction UI because the brightness slider actually scales instead of, say, Dead Space Remake, where it just deletes the test image if you decrease the brightness slider. Both Alan Wake 2 and Callisto Protocol provide multiple gamma settings to ensure the output can be optimized for whatever display the user has. We're veering off from the graphics rendering topic since this is a little more related to UI design, but programming a UI becomes easier when fully developed gamma systems are already present in the engine.